You're ready to get started? Okay, welcome everyone to the Nuclear Science and Security Consortium Alumni Speaker Series. It's my pleasure to introduce our featured speaker today, Dan Hellfeld, who is a Senior Scientific Engineering Associate in the Applied Nuclear Physics program at Lawrence Berkeley National Laboratory. His research interests include fusing radiation detection and imaging methods with contextual sensor data for nuclear security related applications. He obtained his Bachelor of Science at UC Santa Barbara, and then he went on to Texas A&M to get his Master of Sciences before he came to us here at UC Berkeley to obtain his Ph.D. in 2019 in our Department of Nuclear Engineering. And as a Nuclear Science and Security Consortium Fellow. So with that, I think he's well qualified as an alumni to maybe say a few words about his past, how he got to where he is right now, and what he's doing right now in his research at Lawrence Berkeley Lab. Then, with that, all yours.
Thanks, Kai. Let's see if I can share my screen here. Let's try this.
Looks good.
Okay, looks good.
Yep.
Let's see if I can try to see most people while I'm talking here too. Maybe not. Okay. Thanks for bearing with me here. I'm just trying to get myself set up. Okay, yeah. So good morning, everyone. Thanks for having me. So this talk will be pretty informal. I'm just, maybe talk a little bit about myself, how I got to where I am, and then most of the talk will be sort of research highlights over the course of my dissertation at UC Berkeley, as well as some of the work I'm doing right now at LBNL. So the title of my talk is Application of Computer Vision and Gamma Ray Imaging, which is a fairly generic title, but over the years you sort of have talks that do the same thing, and so you kind of have to get clever with your titles, and sometimes it's good and sometimes it's bad, sometimes it's okay. I'd say maybe this one's okay. So, but yeah, like Kai said, things we're working on now and things were my interests during my thesis at UC Berkeley were fusing the data streams that can come out of these contextual sensors, such as Lidar, camera, and fusing them with radiation detectors and imagers to perform 3D imaging in near real time. So that's what this idea of this computer vision aspect of these gamma ray imagers that we're starting to develop here. Okay, so let's jump in here. So I thought I'd take some time to talk about myself, though I don't have too many slides because I don't like talking about myself too much. So then I'll get into this concept of scene data fusion, which is this idea of fusing these different data streams together to enable certain capabilities within the gamma ray imaging domain. And then I'll talk about some of the results and show some nice pretty pictures. And then I'll talk about what's going on now and what's coming up next in terms of my research. So I grew up in Orange County, California. And here I have a picture of the San Onofre nuclear generating station, what they call it. SONGS, San Onofre Nuclear Generating Station. Yeah. So yeah, if anyone read the abstract, I said that I grew up surfing right out front here. It's a very nice state beach, San Onofre State Beach, which has a very nice crumbly break, which is good for longboarding. So there's lots of people that go out and longboard there. And yeah, growing up, I didn't ever really think twice about what was going on at SONGS. I knew it was a nuclear plant. That was about it. But in my young days, I didn't really think twice too much about it. Though, as I grew older and through high school and things, I became very interested in physics. And so I went to UC Santa Barbara to pursue a bachelor's in physics. it's at that point in time, it was still very general. My interests were very general. It was, you know, how do things work at a subatomic or galactic scale, all these things, right? This is the young interested mind in physics. Just everything's interesting. Let's learn about it all. And so here I have a picture of my back patio that I actually got to live at while at Santa Barbara for one of the years. If anybody has been to UC Santa Barbara or seen pictures, it's a very beautiful campus right on the water. And all of the students live in this little town right next to it, which is also on the water. And so some of the houses have back patios that are like this, that are on a cliff overlooking the ocean. And so this was probably the closest I will ever live to the ocean for the rest of my life. And it was a great time. So I tried to make the most of it there, and got to continue surfing while at Santa Barbara. So that was good. But during the course of my physics degree there, it came time to think about what's next, right? And so graduate school was an obvious next step, but I didn't quite know what I wanted to do still. I didn't think that I was quite cut out for a physics PhD. So I thought, you know, what's the next best thing, I guess, right? So engineering came up, and you know, then it started to think back as to you know, what I really would enjoy pursuing and learning about. And you know, I kept coming back to nuclear, which, you know, tied nicely to my upbringing near the Songs plant, and also, you know, growing up watching The Simpsons and seeing Homer Simpson work at a nuclear power plant. That was you know, probably one of the dominant driving factors of me pursuing a nuclear engineering degree, I'd say. But what I really liked about nuclear engineering was that if I was going to leave the physics field and go into engineering, I felt nuclear was a very nice space to go that held on to a lot of interesting physics, and had a good opportunity for me to continue learning physics while applying it in this sort of different engineering domain, I guess. So that eventually brought me to Texas A&M to pursue a master's in nuclear engineering. And so while I was at Texas, I did an internship at Lawrence Livermore Lab, I think in 2014, the first year, I guess, at Texas, and which I worked on this Watchman project, which is a kiloton scale water shrink-off detector that was at the time just a proposal, just a white paper that was supporting most of this work, that they wanted to use to demonstrate remote reactor monitoring. So you can place this giant tank of water several kilometers away from a nuclear power plant, and you can monitor things like, is it on, is it off, what's the power level, you know, maybe you can introspect something about the fuel isotopics inside and how they're evolving in time. And my task when I came in as an intern was to explore a different interaction channel within the detector to see if we could actually use it to point back to the reactor. So the idea is that you could put such a detector in a remote area and be able to find remote clandestine reactors that could possibly be within the sensitive radius around your detector. Or you could think about it, if you have some amount of directionality, you can use that to discriminate your source from your background a little bit. I don't think I actually mentioned that this is a neutrino detector. So this was a, you know, in the depths of the nuclear reactor core, right? There's all of these fissions happening and lots of other reactions that are also happening that produce these antineutrinos, specifically these electron antineutrinos that just are unimpeded and can escape the reactor. The containment vessel, no problem. They can go through the earth, they can go through anything. They're sometimes referred to as ghost particles because the reaction, the dominant cross-section that's used in these detectors, which is this inverse beta decay reaction, the cross-section is, you know, I had to look this up when I was an intern, but it's on the order of zeptobarns, which is like 10 to the minus 21 or something like this, barns, which barns is also 10 to the minus 24, right? So you get pretty low down in these numbers. So it's surprisingly small and it's surprisingly hard to detect these things. And that's why this giant tank of water is the size of a 3-story house. But so I looked at antineutrino electron scattering, which is highly directional, so you can get some idea of where the incident neutrinos are coming from. But the cross section is even lower than inverse beta decay. So the problem there is, do you even have enough signal to see that or to be able to infer some sort of directionality? And through the course of the internship, I became really interested in the project and was actually able to turn it into my master's thesis. And thanks to the NSSC, they were able to actually support me when I was at Texas for the last chunk of my thesis there to work on this project at Lawrence Livermore. So that was really great. And I was able to finish my thesis. Long story short, it's really hard to do neutrino directionality with the electron scattering channel. You have to sit there for multiple years. So you might have better luck with just flying an airplane or something overhead and then using visual imagery, but that's okay. So once that finished, the plan was to potentially keep working on Watchmen, and what better place to do that than to come back to California, to the university that's closer to Lawrence Livermore, which is UC Berkeley. But as I came to UC Berkeley, and I started working with Kai and in his group, in the Bearing group, as well as the applied nuclear physics group up here at LBL, I became much more interested in the gamma ray imaging stuff that they were doing here. And so at some point I decided to leave Watchmen behind and come and work on this new project that was just starting up at LBL, that was to design and build this detector system called PRISM, which I have shown here on the bottom right, which is this, and I'll talk about this a little bit more in detail later, but this is a spherical active coated aperture detector gamma ray imager that can image gamma rays in all directions. And it also has this contextual sensor suite on top. So you can see that there's a Lidar up here and a camera. And I'll talk about more about this later, but the idea is that this is a handheld system that you can walk around and freely move throughout some environment and map the radiation fields in 3 dimensions. So this project was great to work on as a student, because it was very fast paced, and I got to learn how product development works within a lab and things like this. At Livermore, working on Watchmen, I was still very much a grad student working on a sort of separate project from the main Watchmen project, but at PRISM here, I considered myself to be a integral part of the project itself, which I found to be quite rewarding from a grad student perspective, in terms of sort of attaching myself to a funded project with milestones and deliverables and things like this. It's sort of I found it useful to keep me on track and to keep pushing me forward to get more results in throughout the course of my work. But PRISM was great, and it actually was featured as the image here for the Nuclear Science Day at Lawrence Berkeley Lab that they do every year, and it actually won an R&D 100 award. So that's a nice thing that I get to put on my CV. So overall, I think coming from Orange County and sort of moving up the coast and then spending a little bit of time in Texas, but then sort of coming back to California and moving up the coast has been a great experience. And I'll say that starting in 2014 or whatever at Livermore, the NSSC was really able to foster that and to help me get to where I am today. So for that, I'm very thankful and really glad to hear that the next recompetition was awarded again, so we can keep going and getting more people trained up for these types of things. Okay, as an NSSC fellow, I got to travel a lot and present a lot, which was great, both in terms of becoming more comfortable containerizing your work and presenting your work and public speaking and just networking and meeting other people at different places. So over the course of 5 years, I traveled to 4 different continents. I traveled all over the United States. It was great. Some were conferences where I presented. Some were conferences where I just listened. Some were actual courses meant for students to just learn, which I wanted to point out here that I've marked in red. These are these 3 almost summer schools, I think they're called, right, in the NSSC, that when I was a fellow that they encouraged us to attend these summer schools, and these are the three that stuck out to me. So the first one was the PPNT, I think it's Public Policy and Nuclear Threats, I think. The boot camp, I think it was like a week or two long at UC San Diego, and that was a great opportunity to learn about, the policy side of nuclear, as well as, meeting a bunch of other fellows and having fun in San Diego, and really, building relationships that have lasted to this day, right? So I think at PPNT, this is maybe where I met Sarah Laterman, who spoke last time. But after that, Sarah and I were good friends throughout the rest of the graduate studies at UC Berkeley. There was also this International Nuclear Safeguards Policy course at the Monterey Institute of International Studies. I also highly recommend that if anybody has the opportunity to do this. Hopefully soon we can go back to doing these things in person. And then finally, there was this non-destructive assay course at Los Alamos, which is a part of this, I think, this series that they do to actually train IAEA inspectors, or they're sort of modeled after the training that IAEA inspectors go through to learn about most of these technologies and techniques that are used out in the world in real safeguard scenarios. And so I think maybe that is part of the keep-in non-proliferation stuff that the NSSC fellows get to do. Unfortunately, that wasn't a thing when I was there. So I just was able to actually go and just do the course, which was great. Lots of other places that I've been, it was a lot of fun, and got to meet a bunch of people. And like I said, I think the most rewarding part of all of that was building the relationships and the network that I've sort of grown to rely on, I guess, now moving forward in my career, knowing all of these people and being able to talk about all of these interesting things that are going on. Okay, so what do I do now? Like Kai said, I'm a senior scientific engineering associate at the A&P group at LBL. This is the same group I worked in while working on the PRISM project. So this was just a natural progression of when I finished my thesis, I just became a staff member of the group and continued working on similar projects. So now I work on a variety of different things that are funded by a whole bunch of different agencies, including DITRA, which is in the Department of Defense. There's NA22 in Department of Energy, and then there's the CWMD, which is in the Department of Homeland Security. So I work on things like the gamma ray imaging and free moving systems that I mentioned before, but now we're trying to do this in a quantitative way where we can have gamma ray images that have units associated with them, like microcuries or microsieverts per hour or something like this, units that are tangible to users that they can act on, as opposed to, this area is hotter than this area. Working on mobile radiation search in urban environments. So this is a product called MERS or LEMERS, where we have an array of sodium iodide bards in a van with a bunch of other contextual sensors, and this is meant to be driving around urban environments and mapping. There's also anomaly detection and source attribution and radiation sensor networks. So these are static networks of detectors that are placed around large area urban environments, and we can try to detect and track source anomalies as they may be traveling through. And then a newer project now is looking into reinforcement learning for small unattended aerial systems, or SUAS swarms. So we've talked about, or the idea here is to have several of these imaging systems that are compact and put them on drones. And then we have multiple drones that can all fly around and cooperate to both, map the area visually as well as in the gamma ray space. And so we can do this much faster with just one drone, right? Which is what we've done up until this point. So day to day, mostly what I do is I work on software development and data analysis. So we go out and we collect data. We have to, image reconstruction, and we write software to do that image reconstruction, and some amount of algorithm development and things like that. There's also some amount of hardware work that I do. It's pretty minimal. It's more sensor testing and integrating sensors together to build out these packages. But I definitely consider myself more on the software side of things. And then a nice thing here is that at LBL I was able to become a FAA certified remote UAS pilot, which means that I can fly these, big drones that we have, and we can attach these imaging systems to the bottom of them and fly them around. And since I'm doing this for work, I have to be a FAA certified pilot, which is a cool thing to tell people. I sometimes just remove the remote part of it, so I can just say, yeah, I'm a pilot. Sometimes my father-in-law is an actual pilot, and so he loves it when I say that. But that's been really fun. Flying drones is fun. It's also kind of nerve-wracking because most of these systems are quite expensive, so you don't want to crash. But overall, it's been fun, and like I said before, you get to travel to other places for these demonstrations that we've done in the past, where we go out and demonstrate these systems by flying them around these interesting environments and reconstructing in real time. Okay, so that's enough about me. I think I've alluded to a lot of these interesting things that we are working on or have been working on. So I just want to now get into a little bit of that for the next 20 minutes or so, I guess. So here I'll just sort of set the landscape here, where the ability to map radiation distributions in 3 dimensions has lots of applications, ranging from contamination avoidance to directed search to decontamination verification, right? And so the ability to perform such reconstructions with a free moving system facilitates flexibility in the deployment and operation of that system, as well as can expand the scenarios in which such a system could be used. For example, in the consequence management box here, we show the ability to perform a quick handheld measurement where we took a system and walked it around a contaminated home in Fukushima following the nuclear accident in March 2011, which we're very close to coming up on the 10-year anniversary of. And this includes surveying the outside and the inside of the home, and you can build out these contextually detailed, rich data products that show the house, as well as the 3D radiation map on top. So there may also be scenarios in which human operators should be avoided, right? And systems can be mounted onto these ground robots or small UAS in order to distance the humans from the radiation itself. And so you can see here in the directed search box, we've shown that you can mount these systems onto a robot and drive the robot around and find a source. Or, in other boxes here, I've shown that you can mount these on small unmanned aerial systems and fly them around. Finally, I'll say that this free moving capability that we're talking about here, being able to pick a system up or attach it to some other vehicle and just move it freely through some environment in any dimension X, Y, Z, and in rotation, is really powerful and allows us to both overcome the inverse square law from the fall off of the signal from the distance away from the detector by very easily getting close to sources that we may encounter. And it allows us to significantly reduce the time to detect or localize or image by being able to quickly explore a space and get close to source and get enough counts in order to image appropriately, which is quite important in scenarios like the directed search box here, where you may have a source that's somewhere and you don't know where, and you need to find it, and you need to find it now. So you want to be able to quickly move and quickly find, and these types of systems really enable that. So what is this nuclear scene data fusion concept that I keep saying? The idea here is that we have the ability to utilize contextual sensors such as visual cameras, Lidar, and IMUs, or initial measurement units, in conjunction with the radiation sensors on board, right? So the contextual data can be used to perform simultaneous localization and mapping, or SLAM, which is used to track the position and orientation of the system, typically referred to as pose, as well as create a 3D map of the surrounding environment, here represented by things that we call point clouds. So on the right, you can see an example where the contextual sensors on board a small UAS were flown around a small house, and here we show the system trajectory in red. And the white points here are the 3D point cloud model. So you can see that by just flying around these contextual sensors, you can track yourself and you can map the environment around you. And then the idea is that you can fuse this. Oops, why isn't it clicking? There we go. You can fuse this with the radiation data that's streaming in on board if you have a detector or imager also on board, to time correlate the radiation data with our pose estimates in a globally consistent 3D coordinate system, right? So the scene map provides visual context to the image reconstruction and can be used to constrain the reconstruction itself. In other words, we can reconstruct source activity to physical points in space measured by that Lidar, as opposed to fully discretizing the surroundings and reconstructing everywhere. This approach improves imaging accuracy and significantly reduces the imaging time, pushing these types of reconstructions that we can do to what we call near real time, meaning that the reconstructions are on the order of seconds and can provide in situ image updates to the user and allow for the potential for path correction to further decrease the time to image. So as you're flying the system, we can generate these 3D images and provide those to the user, and thus, they have some amount of feedback that they can use to then adjust and go explore other areas that they may find interesting. So how do we do this? The idea is that we've packaged all of this up into a sensor suite that we call the Localization and Mapping Platform, or LAMP. And the idea is that this contextual suite can be paired with anything essentially, right? So the idea is here is it's detector agnostic. It can be paired with CZT detectors, high purity germanium, cesium iodide, CLOBC, lanthanum bromide. The list goes on, right? And you can have commercial systems you can buy off the shelf, or you can have custom made prototype systems that are developed at the lab here. So we've demonstrated all of these capabilities with all of these different types of detector systems. There's dual particle sensitivity in imaging. So we've demonstrated that you can do this type of work with gamma rays and neutrons using certain type of scintillators here, like the CLOBC. It's also platform agnostic. So like I said, right, you can carry it in your hand. You could attach it to some vehicle like a car or a drone or a helicopter or a robot. And lastly, this typically, depending on the system that you have, it enables multimodal image reconstruction, which means we can run proximity-based mapping, which is just using the signal modulation of the system moving towards and away from the potential source. You can have active or passive coded mask imaging, which I'll talk about in a bit, and as well as Compton imaging, which I'll also touch on. And so having this multimodal imaging capability means that you can image bunch of energies over a large range, so around 50 to about 50 keV to about 3 MeV, which is really nice because it encompasses a lot of the potential lines that we care about in the nuclear security domain. Where uranium's at 186 or 1001, or the cesium-137, which is a nice fission product, is at 662 keV, things like that, right? So on the right, I've shown a couple examples here, just example data products of the things that you can do with these types of systems. So on the top, this is a handheld measurement where the PRISM system was walked around a car with the trunk open, and there was a source in the back of the trunk, like a plutonium surrogate source, I believe. And if you look closely, you can see that you can really nicely outline the car, as well as where that hot spot is for the radiation. You can also see some spill out onto the floor, which is not just noise. It's actually just a a downscattering effect of this source. Has a lot of high energy lines, and I was imaging on a low energy line. So these high energy photons can scatter off the top of the trunk or the ground and then hit my detector, and I can think of that as full energy if I'm looking at a low energy line. But depending on the parameters you use in your reconstruction, you can learn a lot about the source and the potentially other lines that you're not necessarily imaging at that very moment. On the bottom, I show an example drone flight where we flew around a moving truck where there was a cobalt-60 source in the top corner, and you can see we were able to track the system as it flies around, map the area around it, and then localize that source with pretty darn good precision here to that top right corner of the truck. Right? So over the years, at LBL, we've developed a whole bunch of different lamp systems, where here on the left, there is this original Hemi detector, which was a coplanar grid CAD zinc telluride, or CPG CZT. We've also looked at cesium iodide, which is this sort of lower resolution scintillator detector. We've demonstrated this with commercial off-the-shelf systems like the H3D Polaris system, which is pixelated CZT, or the Ph.D.'s JEGI system, which is a double-sided germanium strip detector. We have detectors that we've built in-house, like Prism, which is the one I worked on, which is also a CPG CZT detector. There's the mini Prism system, which is also CZT, but the detectors are arranged in a more compact form factor. There's NG lamp, which is this CLOBC detector I talked about before. This is these new El Paso light detectors that are sensitive to both gamma rays and neutrons. There's also lanthanum bromide lamp, which is useful for high rate environments. And I mentioned here up that there's more on the way. So I could say right now, I think there's currently at least five more that are in development. So we're working on the next generation Polaris, the next generation Prism, next generation Mini Prism, NG lamp. And then we're also designing these smaller, lightweight, what we're calling mini lamp systems for that swarm project that I mentioned before. All right, so first, I'll first just give a quick overview of gamma ray imaging. So there's two modalities that we tend to consider here. The first I'll talk about is Compton imaging, which we use Compton kinematics to constrain the source direction of the incident gamma rays to the surface of a cone, right? So if you can track the positions and energy depositions of your gamma ray interaction in a detector or several detectors, you can have some idea of where the source could be constrained to this cone surface. Most of the time, so this diagram here shows 4 interactions, but most of the time we actually only consider there be 2 interactions where you have a Compton scatter followed by a photoelectric absorption. And when you have, typically we call these doubles, and when you have these types of interaction sequences, there tends to be some ambiguity as to which event was first, right? So either R1 or R2, maybe my detector doesn't have the timing resolution to tell the difference. So I need to have some other way of knowing which one was first, because which one was first dictates the vertex of the cone. So either the cone may point this way, or maybe the cone points this way or something. So you don't necessarily know, and what this means is that the sequencing can be ambiguous, and sometimes you have 2 cones that you need to consider. And we have some methods to deal with that, and I'll talk about that in, I think, the next slide. But something to consider here, that there is some interesting things that you can constrain the direction of the incident photon to a cone, but there may be multiple cones. So what do you do with those multiple cones? Second, there's this coded aperture reconstruction technique, which relies on this idea of having this pattern of radiation opaque and transparent elements in front of some sort of position sensitive detector. That pattern will uniquely modulate the gamma ray flux with direction of that flux, right? And so based on this little graphic here, you can see that there's a coded pattern of these open and closed elements. And so an image would then be projected onto this backplane in this coded arrangement. And then you use some reconstruction algorithm to then decode that and produce the real image here. I make a note here about passive versus active masks, where traditionally these masks are made of some high density material that are just active passively, modulating the incoming flux, but don't necessarily do anything else. And in most cases, that's heavy and you lose sensitivity. So why not just use something that can modulate flux while also acting as a detector? So you can just replace the mask elements with more detector elements. And so the detector elements themselves will occlude the backplane detector elements to some degree, while also providing you some sensitivity to events that either scatter in the first plane and deposit in the second plane, which you can then reject from your coded aperture analysis, or you could actually use it for Compton imaging, right? So that plays into this idea of tracking these two events in two different detectors and building out these Compton cones that you can then project into space. So with that, I'll show a little animation here, because traditionally coded aperture is performed in, or Compton imaging is performed in 2D, and the detector system remains static and defines this coordinate system in the far field domain around it. And the measured Compton sequences are converted into cones and then back projected from data space to image space. So as the interactions come in, you can have these cones and they start to overlap in certain areas of space. And the idea is that the overlap of these cones will start to reveal the source direction. And since this is in 2D, you don't think of these as cones, but you can think of these as circles on a sphere. And so you're looking at this circle pixel intersection if your spherical surface here that you're considering is pixelated, and you're projecting these circles from your Compton sequences on top. So here's an example of doing this in practice where you have these cones that get rendered as circles on a plane, and you build up an image over time by projecting these circles, and you eventually start to see, okay, where the actual source is coming from. Now, the trouble with static and 2D imaging here is that depending on the scenario, the dwell times in order to accumulate enough Compton cones to reveal the source location can be on the order of minutes to hours. And this is because you may not know where the source is a priori, and so you don't necessarily know where to put your detector to look at the source. And so you're kind of just sitting and waiting until you collect enough data. So moving into this free-moving 3D imaging approach, the capability of being able to pick up the detector system and continuously move it in 3D overcomes that sensitivity problem inherent in static imagers. And as well, it facilitates the ability to create 3D models of the environment and reconstruct 3D gamma ray images. So if you can track the detector position and orientation in a global 3D voxelized space, now instead of a 2D pixelated space, you now have a 3D voxelized space. And if you can track your system and get those Compton sequences in a globally consistent way, you can still perform the same back projection technique that you had before, but now it's cones in 3D, and you need to take into account that your system can be in a different orientation or a different position in 3 dimensions. And as you do that over time, as your system is moving and you collect data, you can still project them in a coherent way, which would then overlap in 3 dimensions and then reveal the source location in 3D. So now the cone back projection is no longer circle pixel, but now cone voxel intersection. And so typically, and here's a nice actual data product of this, where we have a system walked around a box where the source was inside of the box, and you can see the tracked system pose, as well as the reconstruction of the visual reconstruction of the box from the point cloud, as well as the 3D reconstruction of the gamma ray source. Now, typically, I've been talking about back projection, but we typically use iterative algorithms like maximum likelihood, expectation maximization, in order to improve the image quality over just these simple back projections that I've been talking about. So that's the general overview of gamma ray imaging and scene data fusion that I'm going to talk about now. And so for the rest of the time, I'll just show some cool highlights that we've done with these concepts. So first, I'll have one slide about the PRISM system, which stands for Portable Radiation Imaging Spectroscopy and Mapping, which is this system again that I worked on during my thesis at UC Berkeley. And so this is this handheld free-moving system where we have about 100 cubic centimeters CPG CZT modules inside, arranged in this active coded aperture pattern, so that we can have this coded aperture imaging capability in any direction around the sphere, right? So before I had a simple diagram showing, a plane in front of one plane, in which your field of view is basically just in front of you, where you have a point and shoot type camera. But if you take those two planes, make them both coded, and then form them around a sphere, now you can look in all directions. And so that was this idea of this new active coded aperture, spherical coded aperture, which means we can image omnidirectional, and we still have the ability to do dual mode, meaning we can do coded aperture imaging at the lower energies here that I've showed on this plot, and then Compton imaging for the higher energies where Compton scattering is more prevalent. So I got to work on sort of all stages of this project, coming in, looking at the design of the version 0 system, and then building version 0, and then redesigning for version 1, and then building version 1. And so, over the course of my time, I got to, be involved with putting things together, actually taking data and analyzing data for both of these systems. And that was really great to be a part of that whole process. So various results I got with PRISM that I put into my thesis and I thought would be cool to show here, where one thing I worked on was the optimization of the mask. So the idea is you have this coded arrangement of active detector elements on a sphere. How do you arrange them in such a way to optimize your imaging performance? And so the approach here was to simulate a whole bunch of different patterns and then analyze their imaging performance and then iterate. And so basically I implemented this Great Deluge type algorithm, optimization algorithm, that would iteratively change the mask in such a way, and I could build up to which would be, hopefully a global optimum, but more likely a local optimum. But it's okay. It's a pretty good local optimum, I would say. But you can see over here, over the iteration, right? We ran something like 40,000 simulations here, and we're able to drive this figure of merit metric that I defined down in order to optimize that mask. And we were able to run 40,000 of these because we wrote this interesting little ray tracing code that I'm showing an example here that can just render these things in sub-seconds and get an idea of the response of the detector system at any angle given that mask pattern. And then you can do that for every angle and then change the mask pattern and do it again. And so the idea is you can run these simulations, in less than a second. And so you're able to run many thousands of them to find an optimal mask. You are sacrificing some physics here, but that's okay. This was sort of just a rough idea to get us closer to this global optimum, but not necessarily all the way there. So one result of that was this optimized mask that I've shown here. That's sort of a sphere folded out. And with that, we were able to implement that mask and put the detectors where I thought they should be in the system. And then we were able to perform 2D imaging in all directions. So that's me showing here 4 different directions here. We're able to image a point source quite well within the theoretical angular resolution of the system. And then we were able to pick it up, move it around, and then use this scene data fusion approach to really enable this free moving 3D imaging approach, which again here is that car scenario I showed before, which was one of the sort of main final plots in my thesis, where we could pick up a system, walk it around, and map both visually and in gamma ray space this interesting scenario here. I worked on an algorithm that tried to find point sources more accurately, as opposed to this general approach where you sort of voxelize your space and you look for sources everywhere. You can reformulate the problem to say that I know that I have a point source that's going to be in 1 voxel. How do I reorient my maximum likelihood problem in order to find that? And we got some really cool results out of this, but I think for the sake of time, I don't have really enough to talk about it here. But basically what I'll sort of get to is that you can run this type of algorithm in a discrete space, which is useful for a lot of approaches, as well as in a continuous space, in image space. And if you do it in a continuous image space, you can have this ability to actually look for multiple point sources. So not just 1 point source, you can look for one and then hold that and then look for a new one on top of that. And you can do this in an additive nature and look for multiple point sources. So that's what this figure over here is basically showing, is that we were able to inject 4 sources around a track and localize all 4 of those sources in 3 dimensions with this new type of point source algorithm. But really what I want to touch on is this idea that I'm working on now, which is this quantitative scene data fusion approach, where before we were able to get a rough idea of the detector response, run our 3D imaging algorithms, and generate radiation maps. But the scales, the color scales, right, used to render these things were relative, meaning, this area is hotter than this, but that's all I can tell you. So the idea was takes a lot of time to simulate and benchmark a lot of these simulations with measurement in order to generate system response matrices for these detectors, such that we can quantify their response in units that are useful to us. Namely, that would be in units of effective area. And if you propagate that through the reconstruction process, you can get out, units like microcuries of cesium-137. So you can walk around a room and you can say, oh, I have, 35 microcuries plus or minus 5 microcuries of cesium-137 in this spot here, which is quite useful and very actionable thing for these potential end users to use such a product. So here's a demonstration of that, where we put one of the systems mini prism on a UAS and flew it around a house where we had a millicurie cesium-137 source in the window. So the data products here on the bottom are top-down projections of us flying the drone back and forth in front of this house and reconstructing where we think the source is located. And if you can actually render these things in 3 dimensions and see that, in both this singles case, this coded aperture case, or using the Compton data, you can reconstruct the source in space quite nicely in terms of it's sitting on that windowsill here. You can actually quantify the activity of the source as well. And so this is 1.8 millicuries, and you can see that we actually capture that true activity within our bounds here. So this was like, this was a lot of effort by a lot of people, and this was a nice result showing that we can take this SDF approach, the scene data fusion approach, and push it into this quantitative regime where we can have activity estimates of these point sources that we have found, or potentially now that we're working on distributed sources, that then can be used to guide either some well-informed next step or whatever that you want to do, given that you have this information now. Lastly, I'll talk about some cool stuff I did on another project, which was Lidar object detection. So we have Lidars on these systems. These Lidars are capable of seeing a lot of detail in the surrounding environment in 3D, and you can use that information to detect objects that you know of, like cars or people or bicycles or things like this. And so this was just a demonstration on one of these systems lemurs here, which has a bunch of sodium iodide detectors, as well as a bunch of contextual sensors on top, namely 2 Lidar on both sides of the car. And so you can see here is a snapshot of me actually standing on this sidewalk over here, taking a picture of the lemur system driving by these cars and these 3 people here. And then this is this snapshot of the Lidar object detection algorithm that actually shows that I can put bounding boxes in 3 dimensions around the cars, around the people, and it actually gets me over here on the other side of the road taking that picture, right? So you can actually see that these kind of pictures line up, and that's actually me that it grabbed. So we did this on a car. We also built sort of a standalone package called the Professor, with a different type of Lidar, but namely doing the same thing. And then as things move, you could take those bounding boxes that you get from the detection algorithm and put them into a tracking algorithm and actually start to build out tracks of objects as they move past you. And if you have a radiation detector next to you, right, you can correlate those tracks with the signal in your detector, and you can attribute a potential source that you see in your detector with a track that has gone past you. So that's some work that Matt Marshall, who is a grad student at UC Berkeley, and Kai's group that is working on. But my involvement here was working mainly on the detector side of things. So that was fun. Okay, so more of the ongoing work, right, is this quantitative scene data fusion stuff. And we're looking more at distributed sources now and looking at how do we quantify uncertainty in the distributed source case. We want to push the quantitative SDF approach towards safeguards applications, and we have money to do that in a new system to build out to try to do that. Working on contextually informed networked radiation sensors, looking at detection and attribution of these sensor networks that also have contextual sensors with them, and how we can leverage the contextual sensors with the radiation data. And then, like I said, there's this multi-platform mapping and reconstruction with drone swarms. So how do you do this free moving SDF approach when you have, 5 or 6 systems flying all at once? And can you reconstruct one data product from that? And then a big thing I'm working on now is this big software suite overhaul. So taking a lot of the reconstruction code that I worked on, in my grad school days, and rewriting and refactoring and testing and containerizing all of these things to make it more future-proof as we continue to push these concepts forward. And so this will be a really nice way to, at some point, license this code, and then other people can then actually use this type of this approach with their systems that they've developed on their end. Okay, that's enough from me. I'll acknowledge all of the people that made this possible. So of course, LBL and UC Berkeley and all of the funding agencies. But of course, I have to thank and acknowledge the NSSC for supporting all of this work, and for getting me to where I am now. And so with that, I'll say thank you. Stop talking and take any questions if there's any. Thanks.
Thank you, Dan. I think that was great. All the way from start, a little bit about you and your history and how you get where you are right now, and really talking a little bit about the exciting research you're involved in. And I think before we open for questions, I think it's a really nice example how NSSC can really work successfully with the national lab partners too. I mean, all the way going back to your master work with Lawrence Livermore Lab, and now with the Lawrence Berkeley Lab, and really involving graduate students like you have been in the past in cutting edge research at the national labs, and then become one of the researchers to push cutting edge even further. I think it's a really nice example, and so really thanks for your presentation. So we have a few minutes for questions.
There's been one question asked in the chat from Jason, if we want to look at that one.
Okay. Do you see that, Dan? Can you read it, or you want me to read it? Or Jason, you can speak too, of course.
I think I can see it. By
the mask optimization.
In the mask optimization plot you showed, I was just wondering how much the, say, angular resolution improves from start to finish.
Oh, great question. I don't know off the top of my head. So the idea, what I can tell you is that Q metric was a combination of multiple things. One being, angular resolution. So there was an idea of wanting to balance the sensitivity of the system with its imaging performance, and typically those things trade off with one another, right? So a fully populated sphere would be very sensitive, but the image quality isn't very good because you have a lot of aliasing, because if your sphere is fully populated, one direction may look like another direction, and so your reconstruction suffers. So you want to start removing detectors in order to provide this coded, mask pattern so that you can image well, but then you start to suffer from sensitivity. So the idea was to design this Q metric to balance these two, and really, you may want to have some weight between the two of them, but at that time, we didn't really know what we wanted, or I didn't really know what we wanted. So I just took a simple approach and had them on the same weight, so that, the idea was that you would balance the sensitivity of the system with the imaging performance equally. That was the hope. But yeah, in terms of angular resolution, I don't have a good answer for you. I can tell you though that the first mask that you start with was completely random, and so you don't really expect too much out of that system. And then the optimal mask that we found, that I think the theoretical angular resolution out of that system was something like 7 or 8 degrees or something like this.
Yeah. That sounds about right. And yeah, I mean, very good point in terms of the balance between sensitivity and angular resolution. I mean, the advantage now, you can actually optimize according to both, but a priori, of course, you don't really know where to focus on, and it really depends on the scenario. For example, if you're looking for a weak source, shielded source in a search scenario, might really emphasize more the sensitivity. But if you go more to the mapping, where something has now a strongly distributed source, where sensitivity is not such an issue, because again, you have plenty of radiation around it, and you want to be more specific and more focus more on the resolution, you might choose maybe a little different implementation. emphasizing more the resolution rather than sensitivity. So, I mean, the advantage there is you can potentially even populate the sphere to optimize differently.
Yeah, and that was one thing with the design of Prism, right? They wired it up such that you could put detectors in all 192 available locations that were on that sphere, because we had this idea that maybe you would want to rearrange them, provided you have some scenario that you're concerned about. We never ended up actually rearranging them though, but
yeah. Well, okay. Again, because this is still an R&D experiment. Daniel, I'll get to your question in a second. I just, I mean, one important point is that, as a matter of fact, one version of the hardware and software has been licensed. So, and this is certainly much more now in terms of commercialization into a product where ultimately you want to then really, if you use it, I mean, this is still what we develop in LBL, more still R&D systems, right, to demonstrate more broadly the applicable some of the features. Daniel has a question. Daniel, you want to ask it?
Sure. I was just curious if you could elaborate a little bit, one, on the timescales that are involved when you're running these drone experiments, when you're doing this and trying to, first of all, determine the location and some of those examples that you showed. Is it on the order of like an hour? And then have there been any sort of hide and seek trial runs where you don't know where the source is, but your drone is flying through a busy area and it can be used as security against non-state actors, for example?
Yeah, so the first part of your question, most of the examples that I've shown here are on the order of minutes. So typically the systems itself are battery powered by a single battery, and at most they can run for about an hour. But most of the time we find that you can, efficiently map a pretty large area, tens of thousands of square meters in about a few minutes or less, right? So if you're on a drone, you can fly around 10,000 meters squared and map that area in about 3 to 5 minutes, if that's your goal. And then you start to think about, well, what if I had multiple systems that can map larger areas, cooperatively? So that's something that we're pushing forward. To talk about a hide and seek trial, yeah, I mean, in most cases, when I'm flying a drone, I know where the source is, and I try to do my best to fly it in such a way that I don't know where the source is. But we are moving towards these types of things where we have done demonstrations in the past where, we have our side who are operating the system, and there's the EH&S people, the source handler people that are hiding the source from us, and we've actually done some demonstrations that we have a source unknown to where the location is unknown to us, and we fly around or we walk a system around an area and trying to find that source. And we've been very successful in all of those demonstrations. Something that I think is interesting, that maybe you meant this if you had a hide and seek trial where you had actually the source itself is moving away from you and you're trying to find the source as you're moving as well. And that's a really interesting approach if you're thinking about a busy area or a port or an airport or something like this, where you may be moving and the source also may be moving. And I think that's where this this contextual object detection and tracking and attribution stuff that Matt Marshall, one of Kai's grad students, is working on, where in real time as the system is moving, I can be contextually aware of what's around me, classify and detect and track them as they're moving as well. And so I can have my physics model of my system, and I can know about all the objects around me that are moving, and I can track them and compare that to my physics model, and I can attribute sources to those individual objects themselves. So you can imagine having a system like the Prism system or something, right, being walked around a busy area, and the camera and Lidar on board are able to see, classify, detect, and track all of the moving people around me as well. And whatever radiation detector or signal I have in my system, I can correlate that with those tracks and try to identify and attribute that source to a track itself. And so, and if we can do this fast enough, right, you can display that information to the person walking the system around and say, oh, hey, I think that person wearing that baseball hat and a white shirt that just walked by you might have a source. Why don't you turn around, follow them a little bit, and see if I can confirm my hypothesis or something like that. So that's a really cool, capability that I don't think we've yet demonstrated that, but this is something that I think we can work towards with the current capabilities that we have. And Matt Marshall is certainly working towards that right now, where the example I showed where we've tracked objects moving around a static system is one step, but he's actually used that MER system that I showed previously as well, with that system moving and other systems moving around it, and you can perform the same type of attribution analysis.
Yeah, I mean, just to add that in terms of the hide and seek, so as Dan pointed out, we have done actually demonstration in some of the environments, or like the artificial villages where people hid sources, and we're able to find them within minutes and localize them in 3D in some corners of buildings over really like almost village scale. So that certainly we're in certainly much faster than any other conventional means to search and detect and localize. So yeah. But and in the largest, I think also the demonstration in a more realistic environment. So we were invited to the Levi Stadium here, the 49er Stadium in San Jose, where we actually were able to map the whole stadium and create 3D maps, just as a first step to demonstrate that you can map these and potentially identify and then track people with potentially sources. So we are absolutely getting into that as well, as Dan pointed out. So I think if there are no urgent questions anymore, I think it's time to wrap up. Thanks, Dan, again, for this really nice presentation. And I just want to mention that in 2 weeks, we have David Weiss from Lawrence Livermore Lab as our third speaker in our series of alumni, NSSC alumni. So I'm looking forward to see you there. And of course, if you have more questions for Dan, you should have his email. I think he will be happy to engage further if you have more questions about the technology he's developing. Okay, with that, thanks everyone for tuning in, and I'll see you soon.
Thank you.
Thank you.